Okay, calculus. Let's see. Hold on, I gotta check my notes. So we were doing horizontal and oblique asymptotes section 6.5. At this point in the day, no one has asked me anything about oblique asymptotes yet. That doesn't mean that you won't. It just means I haven't seen it yet. Hold on, I gotta pick up a marker. Sorry. But someone did ask me to go over 3A and G out of horizontal asymptotes. Same section, just a different day's homework. And then I will start into section 6.6. We will go relatively slowly through section 6.6, just because there's quite a bit in it. So we will take a little bit of time to go through it. And like I said, this might actually be a section where a Zoom meeting might be beneficial, depending on whether everybody has a lot of questions or not. I don't know, maybe I'm just an awesome teacher and nobody has questions, but we'll see. But yeah, we could always do a Zoom meeting if we need to, if you're feeling kind of overwhelmed at that section. We'll see how it goes. I'm taking it all day by day, guys. So 3A and G on page 359. Well, hello, Rolly. Rolly, did you come up to visit? Rolly got a hair. Hey, don't attack the old man. That's cruel. Rolly got a haircut. He looks 5 years younger. He's great. Rolly, you want to say hi? Second. Rolly says, I got a haircut. Oh. Rolly says, I got a haircut. I look better. Yeah, I'm a little stressed though, because I don't know what's going on. All right. Off you go, Rolly. Oh, Wicket, don't be a jerk. Okay, so 3A and G. Sorry, a little aside. Page 359 says, find the limit as x approaches infinity. And really, when you find the limit, really what you're finding is, where's the asymptote? Same question. For 3 over x. And whenever the degree on the bottom is bigger than the degree on the top, then automatically, sorry, I'm hot. I was cold, now I'm hot. I can't decide. Maybe I'm getting old and going through menopause. I don't know. It's probably not appropriate to say on YouTube, is it? Anyway, we're all girls. It's okay. So if you have 3 over infinity, think of it this way. If you had 3 divided by 1,000,000, because infinity is a very large number, if you had 3 divided by 1,000,000, you'd have like 0.0000003, right? As close to 0 as you can get. So it's just 0. For G, for 3G, it's 3x squared. No, sorry, it's 3x plus 2, I lie, over x minus 1. And they want the limit as x approaches negative infinity. Again, it doesn't really matter whether there's a negative or a positive on the infinity. Those rules that we talked about for finding the horizontal asymptote apply here. So if the degree on the top is the same as the degree on the bottom, which it is, this would be 3 over 1, right? Because this is to the first, this is to the first, they're equal. So you take the leading coefficients, which would be 3 over 1, 1. Why did I write 3? 1, which is just 3. So that's your limit. Your limit, finding your horizontal asymptote, it's just a difference in language. What you do is exactly the same, all right? So those were the only new questions I had at this point in the day. Again, that could change and that's fine, but there are the answers to those questions. So that didn't take very long. So let's look. I have a dog hair in my mouth after picking up Rolly. Excuse me. So let's look at section 6.6, which is curve sketching. So curve sketching is really just taking all of it, putting it together, and coming up with a basic sketch. It's not going to be perfect, but a basic sketch of the graph based off of information that you figure out without doing a table of values. The whole point of this is so that you don't need a table of values. So we're only going to do 2 examples today, just 2, all right? Example number 1 is on page 362. And right above that, right above example 1, it actually gives you kind of an outline of the steps you should go through to graph this. So it says frame the curve. In other words, if there's any domain restrictions, anything x cannot be, think vertical asymptotes. Are there any of those? Are there any asymptotes? What's the general shape of this graph going to be? If it's an x squared graph, I know it's a parabola. If it's an x cubed graph, I know it's going to be a wave. So just kind of what is the general shape going to look like? Do I know that? Then find the important points. Any intercepts, x-intercepts or y-intercepts. Any local maximums, local minimums, so finding the first derivative and all that stuff. Any points of inflection, does it change from concave up to concave down at any point? And then we add in any details. And again, we'll get that when we do the derivative and second derivative. And then the last thing you do is sketch the curve. Now today I'm really going to be missing my nice, huge whiteboard. When we actually get back to school, when I actually get back to school, you guys are probably graduating and I won't see you again. That's very sad. But when I actually get back to my big whiteboard, I won't know what to do with all that space. All right, so example 1 says y is equal to x cubed minus 6x squared plus 9x. And what they want us to do is they want us to sketch the curve. So what do I know? Because it's an x cubed graph, I know it's got to look something like this in some way. It could be going the other way. I can never do it the other way, but it could be going this way. But an x cubed graph always has that kind of wave shape to it. That's just what an x cubed graph looks like. So that's an x cubed graph, so I know it's going to do that. I know there's no asymptotes because there's no fraction here, so I don't have to worry about vertical asymptotes or horizontal asymptotes or oblique asymptotes. I don't have to worry about asymptotes. So really what I'm going to be looking for is I'm going to be looking for intercepts. I'm going to be looking for local maximums and minimums, and I'm going to be looking for points of inflection. Those are the things I'm going to be looking for. So like I said, we're really just going to be taking all the previous sections and putting them all together into one giant question. All right, so intercepts. Let's talk intercepts first. For intercepts, it's really about finding where is it crossing the x-axis, where is it crossing the y-axis. So for intercepts, I'm going to make my x 0 and I'm going to solve for y. So if I do that, 0 minus 0 plus 0 is going to equal 0. So I'm going to have an intercept at 0 and 0. So when I'm framing my curve, I already know that's a point. Now the one that's generally harder to figure out is what if I make my y 0? Those are my x-intercepts. If I make my y 0, I have x cubed minus 6x squared plus 9x. If I'm going to solve for x here, I'm going to take x out as a common factor, and I would get this, x squared minus 6x plus 9, and then I would factor this to be x minus 3 and x minus 3. So either this x could equal 0 or x minus 3 could equal 0, so x would be 3. This one would be the same, so no need to do it twice. So I have an intercept at 1, 2, 3, and 0. So I've already found intercepts. So now what I'm going to do is I'm going to worry about where is it increasing, where is it decreasing, and do I have any local maximums or any local minimums? So finding areas of increase and decrease and finding local maximums and minimums means you have to find the first derivative. So first derivative would be 3x squared minus, not 6x, minus 12x plus 9. I'd make that equal to 0, and I would take 3 out as a common factor because I could, leaving me with this. And then I would see, can I factor that? I believe I can, because if it's x minus 1 and x minus 3, 3 times 1 makes positive 3, and negative 1 take away 3 makes negative 4. So either x minus 1 equals 0, which means x is 1, or x minus 3 equals 0, which means x is 3. So doing my little table, I would have 1 and 3, and I'm going to check before, in between, and after those to see whether things are increasing or decreasing. So if I choose a number less than 1, and remember you put it back into your derivative. So if I take 1 and I put it back in here, this would be 3 minus 12. Or sorry, I don't put 1 in, I'm going to put 0 in. I got to pick something less than 1. So I'm going to put 0. This would be 0 minus 0 plus 9. I'm going to get a positive, so I know before 1, this graph is increasing. After 1, I'm going to pick a number between 1 and 3, so say 2. And again, it doesn't matter whether you put it into here, where you factored it, or here. It doesn't really make any difference. Whatever you can do fastest in your head or with your calculator is fine. So if I do 2, 2 squared is 4, 4 times 3 is 12. That would be 12 minus 24, which would be negative 12, and then negative 12 plus 9 would give me a negative 3. So it is decreasing. So I have a local max. I have a local max when my x is 1. So I need the y value for that, so I can plot it. So if I put 1 in here, 1 minus 6 is negative 5. Negative 5 plus 9 is going to give me 4. So I'm going to have a maximum at 1 and 4. So I can even put that in if I want. Here's 1, 1, 2, 3, 4. Okay, so that's going to be a local maximum. So now I need to pick a number after 3. So I don't know, maybe 4. And I'm not going to be able to do that one in my head as well. So 4 squared is 16. So 16 times 3 minus 12 times 4, which is 48, plus 9 gives me a positive answer. So it's increasing. So I have a local minimum when my x is 3. So again, I need a y value for that, so I go up here and I put it in. So 3 cubed is 27. 3 squared is 9 times 6 is 54, so minus 54. And 9 times 3 is 27, so plus 27, I get 0. Well, that makes sense because I already knew that my intercept was at 3 and 0. So technically, I didn't even have to do that work. I just didn't pay attention and notice that that was there. So this is actually a minimum. Not only is it an intercept, it's a minimum. All right, so now I have to figure out concave up, concave down, points of inflection. So that's the second derivative. So that's going to be 6x minus 12. I'm going to make that equal to 0. So 12 would be 6x, so x would be 2. Alrighty, so I'm going to pick a number before 2, put it into my second derivative, because this is the second derivative test, and see whether I get a positive or a negative. So if I pick 1, 6 times 1 is 6, take away 12 is a negative answer. So that means it's concave down before 2. So after 2, if I pick, I don't know, 3, 6 times 3 is 18, minus 12 is a positive answer. So it's now concave up. So that means there is an inflection point at 2. So again, I need a y value for that. So I'm going to go back up to my original equation and put 2 into there. So 2 cubed is 8. 2 squared is 4 times 6 is 24. Plus 9 times 2, which is 18. I get 2. So at 1, 2, and 1, 2, at 2 and 2, there is an inflection point. All right. Now, before 2, it is concave down. And notice, up until 1, it's increasing. So up until I get here, the graph is increasing, which makes sense because it's got to go from here to here, right? So that's increasing because left to right. So it looks like it's doing that. And then coming down. So all of that is concave down because it's making that upside down U shape. And again, nothing really dramatic happens at an inflection point. It is just mathematically where it starts to change direction to turn to go the other way. And it doesn't necessarily make a big sharp turn. And so nothing, you couldn't necessarily identify an inflection point if it wasn't labeled and if you didn't do the math to find it. You wouldn't be able to pinpoint. That's the point at which it starts changing. Even think about going down a road. If it's straight and all of a sudden it starts, not all of a sudden, but if it's straight and it gradually starts to turn, you may not be able to tell me the exact moment when that turn started. You can tell you're turning, but you may not be able to tell the exact moment when it went from being straight to starting to curve inward. You may not be able to tell that. So an inflection point, while we label it, while we find it, when you are graphing it, nothing dramatic happens there. But this is a local minimum, so I know it's going to turn to be concave up. And so, again, nothing really dramatic happens at that point of inflection. And in fact, I kind of overemphasized it. Really, nothing happens there. Okay? And so they have a picture of that on page 363. So just to recap, this is just putting everything together. First thing I did was find intercepts, x-intercepts and y-intercepts. What I will tell you is if it becomes very, very complicated to figure out, especially the x-intercept, don't bother with it. Like if you're all of a sudden going to have to do like synthetic division and you're going to have to do all this really complicated stuff to figure it out, then you don't need to. All right, really just find it if it's something pretty straightforward. This one was pretty straightforward to find. If you start doing it and you find, oh my word, finding this is insane, then don't do it. Usually making the x 0 is really easy to do. Are you okay down there? I seem to have a dog freaking out. Willow, are you all right, baby? You can't come upstairs. It's okay. You don't need to be up here with me. Okay, so Chris isn't home, so she's all alone, and that's not okay with her. All right, so, and she's kind of clumsy and kind of crazy, and steps are not her friend anymore. This is what the graph would look like. Oh, I know, I was talking about intercepts. So find them if you can, if they're not insane to find. Then we find maximums and minimums, points of inflection. I make these little tables so that I can kind of, like this already told me the basic shape of the graph. It was going to go up, come down, go back up, right? It's going to come up, go down, go back up. It already gave me the general shape of what the graph was going to look like. So that's why I do it the way I do it with these little tables. They don't necessarily do that in the textbook. I do, just because it just helps me get a better visual in my head. That's all. All right. You know how I have black marks on my wall at school because every once in a while I by accident hit the wall? I'm going to have that in my house. I'm not okay with that in my house. It's my house. I have to repaint this wall. All right. I don't think the school would pay to repaint my walls because I'm stupid and don't put the cover on my marker. All right, example 2. Do you guys get annoyed with me rambling? I'm sorry. Example 2. Sketch the graph of the function f at x is x squared over 1 minus x squared. So this one is a fraction. So there are going to be asymptotes. So in this one, I'm not going to worry as much about things like where is it increasing, where is it decreasing, finding the first derivative, finding the second derivative. That's not for questions like this. All of that work is for stuff that is linear, stuff that is straight lines without asymptotes. That's what you do with that. When you have a fraction and you have asymptotes, you don't really need to do the let's find the first derivative, let's find the second derivative, although they do that in the textbook. I'm telling you, there really isn't a need for that most of the time. Let's frame this curve a little bit. So let's first tell the dogs to be quiet. Hey, enough. Okay, so let's find intercepts if we can. So intercepts. So the first thing I'm going to do is I'm going to let x be 0 and I'm going to figure out what my y is. So if this was 0 over 1 minus 0 squared, that is still 0. So I already know I have an intercept at 0 and 0. Now, what about if my y is 0? So I do 0 is equal to x squared over 1 minus x squared. Well, the only thing I can do with a fraction is get rid of the denominator by multiplying so that they cancel, which means I multiply this side by 1 minus x squared. So I have 0 is equal to x squared, so take the square root. I still just get 0 and 0. So the only place where it is going to cross or touch either the x or the y-axis is right here. That's it. So now I'm going to talk about asymptotes. I'm going to figure out vertical asymptotes and if there's any horizontal asymptotes or if there's any oblique asymptotes. I'm going to talk about those. So let's start with vertical asymptotes. Vertical asymptotes happen when the bottom is 0. So when would the bottom, the 1 minus x squared, when would it be 0? Well, 1 would equal x squared. I'll take the square root of both sides. And x would be, and it's important that you say plus or minus 1 because that means there are actually 2 vertical asymptotes. There is one at negative 1 and there is one at positive 1. All right, now we need to talk about, are there any horizontal asymptotes? Well, I know if the degree on the bottom is bigger than the degree on the top, then there's a horizontal asymptote at 0. That's not the case here. I know if the degree on the top is the same as the degree on the bottom, then there is a horizontal asymptote, and I have to look at the leading coefficients. So, if you don't like it this way, where the x squared, think of it this way, negative x squared plus 1. So all I did was make sure that the x squareds were lined up. But that negative goes with the x squared. Don't say x squared minus 1, because the 1 isn't minus, the x squared is. So if I look at the leading coefficients, it's 1 over negative 1, which means there is a horizontal asymptote when y negative 1. So here, at a height of negative 1, there is a horizontal asymptote. Okay? So what else can I do with this? Like I said, they do in the textbook do first derivative and second derivative. I don't really see a need to do all that. Here's what you can do. So I said no table of values, but in a way, I'm going to do a table of values. I'm going to show it to you as a table of values. I don't actually write one out when I do it. I just sit and work it out on my calculator. But I'm going to write it as a table of values just so you can see what it is I'm doing. I'm going to try and make it a little bit more visual. I'm cold again. See, I can't decide. I have a vertical asymptote at negative 1. So if I have a vertical asymptote at negative 1, I cannot make my x negative 1, but I can make it something on the left-hand side of negative 1, but close to it, which would be negative 1.1, and I can make something close to it on that side, which would be negative 0.9. Same thing with the other vertical asymptote. I can't pick 1, but I could do 0.9. And I could do something on the right-hand side, which would be 1.1. What I'm going to do is I'm going to see what kind of answers would I get for that. In other words, what am I approaching? What is my graph getting close to as my graph gets close to those asymptotes? So if I do negative 1.1, negative 1.1 squared is negative 1, is 1.21. It's positive 1.21. Whenever you square a negative, it's positive, right? So it's 1.21, and this would be 1 minus 1.21, so that would be negative 0.21. So I'm going to divide by negative 0.21. I get negative 5.8. Now again, if I had chosen, let me use proper grammar, if I had chosen something even close, like 1.01, something even closer to that negative 1, I would have gotten an even lower number than that. I would have gotten negative 58. So the closer you go to that asymptote, the better actually. It'll give you a better clue. So, but even at negative 5.8, that means it's down here somewhere. So the closer I get to the asymptote, the lower it's going. I don't need to do any more of a table of values to know what's happening, because if it's going this way in this direction, that means it has to be going this way as I go in this direction, but it can't cross that horizontal asymptote, right? So it's going to do that. So now I'm going to do negative 0.9. So 0.9 squared is 0.81, and 1 minus 0.81 is 0.19. So 0.81 divided by 0.19, I get 4.26. And again, if I had chosen something even closer, like 0.99, I would have gotten like 42 or something as my answer. I would have gotten something even bigger. So again, the closer you get to that negative 1, the better. So on this side of the asymptote, my answer is increasingly higher, so very different from this side. I'm going to leave that there for a second, and I'm going to go to positive 0.9. Turns out it's exactly the same when I put it back in here. Same answer. So again, on this side, the closer I get to this asymptote, the higher it goes. Now I already know that that's an intercept, so it's actually going to come down, and once it hits this, it's got to turn and come back up, so I've got this U shape in the middle. So now I'm going to do 1.1. Well, turns out it is the same as this one, and it's negative 5.8. Wicket, stop spinning. And it's negative 5.8. So it's down here somewhere. So again, the closer I come into this asymptote, the lower it's going to go. So the further I get away from the asymptote, the higher it's going to go. But again, cannot cross that horizontal asymptote, so it's got to start to turn. So I've sketched it. I didn't have to do a first derivative or a second derivative, although they do it. You don't really need to though. All right, so it's just a sketch, that's all. So I'm not going to do any more examples today, but I do want to look at the homework with you because one of the questions I'm going to give you, I always get people asking me what it is you're supposed to do with it. So I want to look at that with you. So if you don't have your textbook open, pause this video, get your textbook, open it up to page 370, because you're going to want to look at it with me, all right, so that you can see what I'm talking about, all right? So I really like this question. I don't know why, I just do. I like this question, but most people get really angry at me about it. So it doesn't actually require you to really do any work at all. So Willow, stop. So for number 1, at the bottom of page 370, it says match the graphs opposite with the function below using your knowledge of limit and asymptote. So at the bottom of page 370, they give you 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. They give you 12 different equations. On page 371, they give you pictures of 12 different graphs. This is a matching question. What you have to do is you have to match the equation with the appropriate graph. So I'm going to do the first one with you, all right? So for 1a, it says 1 over x minus 2. So what I have to do is I have to use my knowledge of what that graph would look like to find the appropriate one on the other side. So let me think about that. First off, there would be a vertical asymptote where x is equal to 2, because 2 take away 2 would give me 0. That would be the only vertical asymptote. There wouldn't be any other one. So when I look over on page 371, it could be graph number 1, but it could not be graph number 2, because graph number 2 has 2 vertical asymptotes. Couldn't be 3, couldn't be 4, could be 5, could be 6, could be 7, could be 8, could be 9, could be 10, maybe, I don't know yet, could be 11, but could not be 12. So I've already knocked a bunch of them off the list, and all I've done is find one vertical asymptote. So now I need to figure out, is there a horizontal asymptote or an oblique asymptote? Well, the degree on the bottom is bigger than the degree on the top. That means that you automatically have a horizontal asymptote at y is equal to 0. Based on those rules that we talked about in section 6.5. There is no oblique asymptote, because the oblique asymptote happens when the degree on the top is 1 more than the degree on the bottom, and that's not the case here. So can I knock this down even more? It's got to have a horizontal asymptote at 0. So again, could still be 1, could still be 5, could still be 6, could still be 7, couldn't be 8 though anymore. 8's knocked off the list. Could be 9, could not be 10 though, because 10 has an oblique asymptote. Hey! I think my husband's home. And 11 has an oblique asymptote as well, so that one's off the list. So I've knocked a couple more off the list just by figuring out where the horizontal asymptote was and the fact that there's no oblique asymptote. Shush. So now what I have to figure out is, excuse me, is there any x or y intercepts? If I make my x 0, he is home at the door. You can go see? You can go see, Wicket. If I make my x, he's not gonna let me talk. Go see, go on, go see. Come here. All right, come here. Okay. If I make my x 0, then I have 0 take away 2, which is negative 2. So I have negative a half. So at 0, it should be at negative a half. So again, that may help me. And then what I would do is I would figure out what is happening close to the vertical asymptote. So I would do maybe 1.9 and 2.1. If I do that my x is 1.9, 1.9 take away 2 is negative 0.1. 1 divided by negative 0.1 is negative 10. So it's doing this, right? And then if I do something on the other side, like 2.1, 2.1 minus 2 is 0.1. 1 divided by 0.1 is positive 10. So it's headed up this way. So do I have a graph on page 371 that looks like that one? That's not number 1. I had knocked off those other ones. That is not number 5. That to me looks like it is number 6. So equation A is graph 6. So now when you go to do equation B, you already know it's not 6. You can knock that off the list because it's matching. You can't use a graph twice. So it's a matching question. So the further you go, actually, the easier it gets because you have less and less choices, right? But that's how you go about doing that one. Number 2 is another one I get a question about a lot, and I'm going to assign it to you. So you kind of need to know what to do with it because historically people look at it and go, I don't get it. So for number 2, it says, Jessica was sketching the graph of a function, but she didn't have time to finish it. She lost some of her notes because she's disorganized like me, including the formula for the function, but she still has all the information below. So you are going to take the information and you're going to sketch the graph. So I'm going to start with just the very first couple of lines. The first line says the domain of the function is all real numbers except x is equal to 1 and x is equal to negative 1. So already they're telling you it can't be x is equal to 1, so there has to be 1 there, and x is equal to negative 1, so there has to be a vertical asymptote there. So they're already giving you some information, and then there's information for that. You just keep following through the steps and draw what they tell you. I will go over that one for homework because it is going to require a graph for your homework. Anything that requires graphing for your homework, I will go over. All right? I don't think any of the other ones, I think the other ones are pretty straightforward. They're very much like the examples I went over. So give those a try, see how it goes. If we need to take a day and just review everything, we can do that. If this all goes great, then wonderful. We can keep trying with this section because we certainly haven't finished this section, but we do have a good start on it, okay? And again, after this section, there's 2 more sections, which is all word problems, yay. And then we will be done chapter 6, all right? So I'll talk to you again soon.